Welcome back to MATA02, the magic of numbers. Today, we are going to start seeing some of the payoff of all of the math we've been doing all semester. But to do that, we're first going to have to introduce encryption, codes, what you really mean whenever you're trying to send secure messages, and just some of the basic formalisms around that. So for those of you who haven't already picked one up, I have a small handout near the down here. It's also available on the website if you're looking at this online. That will be useful in the interactive part of today's lecture. So just keep that in mind. Okay, so what are encryption and codes for? So to start, let's start by talking about, give a little story of communication. So let's suppose that we have one character, let's call her Alice, and she wants to communicate with another character. Let's call him Bob. So now, of course, if they're just communicating with each other, oh, sorry, let me get my pen out. So they can just send messages back and forth, and then they're both happy, right? So they're sending messages back and forth, and they're able to communicate. But now, let's suppose there's a third character. Let's call her, and for the purposes of our discussion today, Bob can refer to other institutions. So it could also be a bank, for example. But now let's suppose that there's a third character in the story. Let's call her Eve. Eve is not actually one of the parties of the conversation, but she's trying to eavesdrop, which is why we call her Eve. So this is the eavesdropper. And you'll notice that we named Alice and Bob because those are A and B. So if you read a lot of cryptography textbooks, they'll usually have these particular characters. So it's usually Alice and Bob trying to talk to each other. Sometimes they'll be trying to talk to a Carol as well, with various other characters trying to break the communication or trying to eavesdrop. And so that's what Eve here is doing. And so what Eve is doing is Eve is trying to extract, trying to listen in on this message to figure out what they're saying. So maybe, for example, Alice is you, and you're on an internet shopping site, and the shopping site is Bob, and you're communicating, and you want to send them your credit card info. Now, Eve might be some malicious hacker who's trying to intercept your credit card info so they can steal your identity and finances. So now that's not good. And if you're Alice and Bob, you want to have some way of talking to each other so that you can ensure that you don't actually get all your information stolen. So how do you do that? And there are many ways that you might consider doing this. And we'll start by giving some of the sort of historical ways that people have done this, as well as a couple examples of ways that people have done a little bit more recently. Okay. So that's the basic story. Alice and Bob are trying to talk to each other, but Eve is trying to eavesdrop. Note that in this particular attack scenario, Eve is not doing anything active. So Eve is just listening in. There are other attack scenarios where we have another character that maliciously attacks things, but we're not going to worry about that for now. Just Eve is listening at the door, trying to hear what Alice and Bob are saying to each other. Okay, so when we were talking about the message, though, you have to be a little bit precise about what a message actually is, right? So, of course, you could send a letter to someone, and that's a message. But whenever you're using computers, which most of you here do use computers on occasion, if only to submit things to CrowdMark. So one way of thinking about it is, well, you can encode letters as numbers, and we know how to work with numbers. That's what we've been working with all semester. So, well, you could just do a very simple encoding. A, B, C, D, E, F, G would be 1, 2, 3, 4, 5. All the way through 26. This is a fairly simple encoding, but it gets the job done, right? For the record, if you're actually into computers, you may have heard of this thing called ASCII, which is a more complicated encoding, which has a bunch of other characters involved. And so this is the thing down here. ASCII is actually what your computers use to encode letters and numbers and things like that. So, but we're not going to work with that, though it isn't pretty equivalent. Just because it's a little bit more complicated, but if you're actually doing computer programming, that would be what you would use. Instead, we're just going to worry ourselves about the simpler sort of decimal encoding of the alphabet, the letter decimal encoding. So to make sure everyone's awake, let's try it out. Let's try this out. So I'm going to ask you to match each of these phrases to one of these images, these three images here. So which one of these phrases, so they won't necessarily be the text on the image, but I want you to match these images to these messages. using this encoding table that we have. Basically what we're trying to do, so let's start with the first one. So which one does the first one correspond to? For the record, yes, C is the meme that was posted in the chat on Monday. I'm basically putting this here to prove to you that I did actually go back and look at it. Okay, so it looks like there are, and this meme, of course, with respect to the liars and witnesses that we were talking about with Fermat primality testing. But yeah, so this is pretty easy to figure out, right? So you just have to match things in. So you have a 25, which is a Y, so Y. And then the 15, which is an O. Let's see, 21 is a U. And let's see, and then 18 is an R, 5 is an E, 1 is obviously an A, L, I, A, R, O, and E. Okay, so it's pretty easy to just do this encoding. It's just looking up things on the table. It's just a plain substitution. Just to make sure we're all on the same page, let's do the next couple. So what would the second one correspond to? Note that the other two aren't going to be the text that's in the images. Well, in A, I don't even have any text in there. So what would the second one here correspond to? So you may have to actually work through it all because I'm not just looking at text in the image. Oh, could I turn up more of the lights? Yes, I can. Is that better? Try not to fall asleep. I will be making you guys get up in a little bit anyway, so I'm not too worried about you all falling asleep today. Okay, so excuse me. Okay, so it looks like a couple people have started replying. Well, what does this correspond to? Well, 14 is an N, right? But of course, that N is the same on both of these, so it doesn't really help you too much. What is 21? That's U. 13 is M. 2 is B. 12 is L. 9 is I. 20 is T, so we have two of those. 12 is again L, E, B, U, and G. Yeah, so we have a picture of a dumb little bug over there in B to the right. And well, I had to throw in A somehow. So you guys can go ahead and vote for A if you want. It is the last one. And as you might expect, that is a phrase that hopefully you all, if you've been on the internet for a bit, probably recognize. So let's just never gonna give. And I left off the E because I wanted all three of these to be the same length, but never gonna give you up, and so on. Okay, so that's just the simple encoding, right? So that doesn't really do much encryption because you're just like, oh, well, you look at the number, you look at the letter, and it doesn't really hide the information because it's the straightforward translation. But it turns out that there are ways of extending this so that it is an encryption of sorts. One way is instead of having the normal translation, you might have a more complicated translation where you just pick a random number to assign each letter to, and that would make things slightly harder. We're going to do a slightly easier version of that, which is we're going to talk about the Caesar cipher. And this is going to make use of some of the modular arithmetic that we've been dealing with in this class. And so this was done by, So this was Julius Caesar, who some of you may have heard of, Gaius Julius Caesar. His death date was just a couple weeks ago on the Ides of March, and so on. But anyway, he was a Roman general, among other things. And one thing that he did is he had to communicate with Roman Caesar, and he had to communicate with his generals in the field. And so when he was sending messages back and forth, he didn't want them to be intercepted. And so he didn't want to just write them in plain text. And so he used a couple of different encryptions, but one of the ones that's best known today is this Caesar shift. So the Caesar cipher. And what you do is you just add in mod 26 arithmetic, or equivalently shift all letters by the same amount. So for example, let's say you shift, the one he actually used most commonly was he'd shift an A to a D. So this would just be shifting from 1, since A is 1, remember, to 1 plus 3. which is of course 4 mod 26. B would go to E, so that's 2 to 2 plus 3 is 5 mod 26. And you can see this if you're looking at this in terms of the circle of modular arithmetic, because maybe you have, let's call Z is 26 or 0. And then you have A, which is 1, B, which is 2, C, which is 3, and so on, all the way to Y, which is 25, and Z, which is 26. And so if you keep on going, this is, of course, ordinary modular arithmetic, instead of labeling using 0 through 25, we're labeling through using A to Z. Let's see, so Y, well, you go 3 steps. So that's 1, 2, 3. You go to B. And that makes sense, right? Because Y is 25, which goes to 25 plus 3, which is 28. But of course, 28 is just 2 mod 26. And Z goes to C. So that's 26. But of course, 26 is just 0. So that goes to 0 plus 3, which is 3 mod 26. Okay, and so the basic Caesar shift of 3. And we're going to call this value the key, because you need to know how much you're shifting by in order to figure out what, in order to encrypt and decrypt, right? So let's have you all try it out. So which of these is an encryption of, I am the very motto of a modern major general, using a Caesar shift of shift 10. Grab one of these tables for myself. So of course, in order to do this, you have to first convert it into numbers, add 10, and then convert it back into letters. And so what do we get? So let's just do the first couple letters, and it looks like you all have managed to figure most of it out. So let's see, I is 9, right? And A is 1, and M is 13, T is 20, H is 8, and E is 5. So that would go to 19, 11, 23, 30, but 30 is just, of course, 4, 28, which is, of course, 2, and 15. And when you convert that back, 19 is S, 11 would be K, 23 would be W, 4 is, of course, D, 2 is, of course, wait, did I do that wrong? Oh, yes, I did that wrong. So someone should have caught me. So that was 18, not 28. Wait a moment. Yes, that was 18. And so 18 goes to, looking on the table, that's R. And 15 goes to O. And so it is indeed B down here. Okay, that all seems hopefully fairly easy so far. How do you decrypt? Well, you just do it, you just go backwards, right? So if you have the key, then instead of adding 10, you just subtract 10. But now the question is, how do you decrypt if you don't have the key? So if you were eavesdropping on your friend and their bank communicating, how would you break into their security? Well, hopefully don't do that. That's not being a very good friend. But if you were wanting to do that, how would you do that? And it turns out that, unfortunately, the Caesar shift is actually a very, very easy to break decryption. There are a couple of different things you could do. So for example, if I gave you this particular line, how would you decrypt it? Well, one thing you could do is you could brute force all the possibilities. There are only 26 different keys, and one of them is trivial, so it's pretty easy to figure out when you get the right decryption. Another thing you could do, though, and this starts getting into the field of cryptanalysis, of using statistical techniques to break these codes. You can make use of common letters. So, for example, many of you will have seen Wheel of Fortune before, or maybe you've seen other sort of word games like Wordle and things like that. And one of the things that's common to them is well, one very useful fact is that in the English language, certain letters are a lot more common, such as R, S, T, L, N, E. Those are all very, very common letters. In fact, we can chart out the distribution. So this is on your handouts as well. This is just the distribution of the letters that are common in the English language. So if I give you a Caesar shift of something that's in English, you might be like, oh, well, I can figure that out because even though these numbers don't correspond to the right things anymore, I can still look at the numbers and see what the frequencies are. And if your text is long enough, then, well, whatever encodes the E should be one of the most frequent things. Excuse me. So let's try breaking this code, right? So I gave you this particular Caesar shift encoded text, but it didn't tell you what the shift was. So of course you could sit down and try every single one of the shifts one by one, and you would get the right answer. But that may not be necessarily the best, or the easiest way of going about it. So another thing you could do is you can break it by looking at the frequencies, the histogram of all these letters. So if you count up the letters, it turns out there are 8 Ds, D as in dogs, in this particular text. There are 6 Cs, as in cat, and then we have a bunch of other letters. So there are 5 O's, 4 S's, and so on. So one thing that you might notice is if you look here, C and D are 2 letters next to each other that are both common. So we have 2 common letters next to each other, right? So the 2 most common letters we know are next to each other. But now you can look at this frequency chart and you can be like, well, how often do you have 2 common letters next to each other? Well, that happens here, right? And it also happens here. And well, they have 3 letters that are all reasonably common over there. So like those could all be, there's some amount of randomness. And so that it could also be that. And then you might say, oh, well, and then I have another common letter that's all by itself. So we have an isolated common letter. Because you'll notice that N and P, the letters next to it, are both not very common. And so you might be like, well, where do I have isolated common letters? Well, we have one here and you have one there. Okay, does everyone follow so far? So basically you're just looking at these letter frequencies and then you can be like, oh, wait a moment. So I know that C and D, let me do that in red. C and D are 3 and 4, right? At least, and we know that O is 15. So how far apart are these? So what's the separation? Separation is about, well, it's 11 to 12, depending on whether you're counting from the 3 or the 4. So now, one of the things you can do is you can look at the frequency chart and you can be like, well, how often do you get a pair that are fairly frequent and a single one that's fairly frequent about 11 or 12 away from each other? Well, let's take a look. So if you start here and you go 11, oh, let me draw this a little bit further up so I don't run into things. So if I start here and I go 11, I go right here. So well, that seems sort of reasonable, right? So you go 11 and you come up onto something else that's fairly frequent. You start here, let's say you start here, and you do the same thing and you end up at Z, which is really not frequent. So you know that's not a good starting point. And you start here and you end up going to there. So that E, which is extremely frequent. And so from this, you might be like, oh, well, there aren't that many different possibilities. So I could check all 26 possibilities, but if I look at this, I know where the more frequent things are. And so those more frequent things ought to correspond to the more frequent things in a histogram of English letters, assuming you know that it starts in English. And so one thing you might guess is you might guess that O in the encrypted text is actually E, and C and D are actually S and T. So this is a shift of 10 or 16, depending on if you're going forward or backward. And indeed, we can try that out. One of the ways this looks a little bit like Wheel of Fortune is you don't even have to do the shift for all of them at the same time. You can just start by looking at the letters that you think to be true. So for example, this D should be going to T. So everywhere I see a D, I should go to a T. So T, 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 T. And everywhere I see a C, I should go to S. So S, S, S. Oh, wait, sorry. That's not an S. Anytime I see a C, I should go to S. So C is an S, C is an S, C is an S. Did I miss any? Oh, there's one. And if you guessed O is an E. So if you get the most common letters, sort of like with Wheel of Fortune or with Wordle, things get a lot easier. Let's see, O goes to E. So there's an E layer. E, 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 E. Okay. And so from this, you might start saying, oh, well, this does sort of look reasonable. And then you look to see what the shift number is, because of course the key is just a single number. And it turns out that this ends up giving, it was the best of times, it was the worst of times. And so this is a famous English quote. And because I gave you the information that it started, that the text was in English. So for example, if you were using this to encode Mandarin, well, it would be a whole lot more complicated because the frequencies of words are quite different in Mandarin than they are in English. I mean, they don't even use the same alphabet, so you'd have to come up with some other different encoding. But I mean, the same would be true if you were doing this in Spanish or French, which both use the same letter alphabet. You'd have to use the distribution of those letter frequencies there instead of in English. This is one of the reasons why in my message to you a couple of days ago, I asked you to prepare an English text, because it'll be easier to cryptanalyze with the statistical techniques we have here. Okay, use Mandarin for passwords. Unfortunately, it turns out that there are a lot of Mandarin speakers in this world. And so the hackers know that, and so they have all the frequency distributions for Mandarin as well as for English. Okay, any questions about all that so far? So this is the basic code, one of the simplest ones, as well as I've now given you a way of breaking the code. So, which is to look at these letter frequencies. Okay, if not, then we're going to do an in-class exercise. And there are probably going to be several in-class exercises today, so it's not going to be one big session. So what are we going to do? I'm going to break you up into clusters of, say, around 10 students, plus or minus. So not too many students, because I want everyone to be doing some amount of work. And then we're going to split each of those clusters into two smaller subgroups. And in each group, we'll write two messages. So an English message encrypted with Caesar ciphers using two different shifts. So you will you'll encode two different messages with different shifts. Ideally, about at least 100 characters, because otherwise it'll be hard for people to use statistical analysis. So say 100 characters at least. And then you're going to give the other group both of the messages and tell them the key to only one of them. So in this case, when you tell them both the key and the message, it's as if you're Alice talking to Bob. So you're sharing the key and you're just sending it, so it's easy to decrypt. But in the other case, you don't tell them the key, and so it's as if the other group is pretending to be Eve. They've eavesdropped on the message, but don't have the key. And the goal is then to decrypt both messages. And whichever of your groups decrypts both messages first gets a mango gummy prize. Yes, I know it's not a very exciting prize, but I realized last night that I should have some kind of prize, and so, but I just happen to have these mango gummies. Why did you choose a shift by 16? Oh yeah, that's a very good question. It's because a shift, what I did is I guessed that S and T were D and were C and D, and that corresponds to a shift of 16. So I guess the most frequent things might correspond to the most frequent things in the English language. Okay, so having said that, let's go ahead and get up, break up into groups. If you are online, obviously you aren't going to be able to break up into groups the same way. Instead, what I'm going to do is I'm going to ask the people who are online to do this exercise on their own, except what you'll do is you'll submit your particular text passage into the chat, and then you'll also be working on someone else's text passage in the chat. Okay, having said that, let me turn the lights back on and let's have at it. So for those of you following along online, it looks like someone has put a message in the chat. It looks like a very repetitive message, so hopefully it's not too hard to figure out, but you should try cryptanalyzing that if you're following along in chat and haven't started doing these yet. Has anyone in chat figured out the decryptions for these things yet? Otherwise, I'll have to go back after class and figure out and decrypt all these myself. So hopefully by this point, everyone has 2 different quotes. If they're not exactly 100 characters, don't worry so much about it. Just make sure they're long enough that people can have a chance of decrypting it. Or rather, make sure the longer one is the one you don't give the key for if you have one that's slightly shorter. And so hopefully you're along that way. Let's aim to give the text to your counterpart group at, say, a little bit past 10 o'clock. So hopefully by then you'll have written down your encrypted both your encrypted messages. Grr, grr, grr. So hopefully everyone's slowly starting to finish up. Since it's 10 o'clock anyway, I'm going to go ahead and give everyone a 7 or 8 minute break. If you haven't finished up, please try to finish up. After the break, we will give the messages to each other to start decrypting. So this is officially your break, even though I know for an interactive class, it isn't as obvious what's a break and what's not. So, hi everyone. Welcome back after the break. Hopefully, is everyone back? I know you guys switched seats again, so I'm not actually sure if everyone's back, but hopefully everyone is. Is any group not done writing both the messages for the other subgroup? Okay, well, please do that in the next 2 minutes or so. Okay, so I know not everyone is entirely done, but hopefully you're at a point where you've at least converted it into the numbers that have been shifted. And so if you're at that point, that's fine. You'll just be handing lat instead of the actual letters back to the other group. It'll make life a little bit easier for them since they won't have to convert the letters back into numbers again. So at this point, make sure on one of your messages, you have written down the key to make it easy. And on the other one, you have not written down the key. Please give it over to your counterpart group, and we'll start with the decryption. One other thing. So as you solve each other's quotes or passages, why don't you put them in chat so that everyone can see what people chose as their quotes? Let's see. I saw a message in the Zoom chat, but I can't bring up the Zoom chat right now. So sorry about that. I didn't quite catch it. Well, it looks like in chat we have some people who are extremely good at this. So. I see someone in chat did a quite hard one. How much would a woodchuck chuck? Because that doesn't have any E's or T's. And so if you want to make really hard things, you can do things that have really weird frequencies, like the last example in chat. Oh, well, you should remember, everyone, that the key of -4 is the same as the key of 22. So, yeah, just responding to some of the things people are saying in chat. So I know that not everyone's done and that people are still working on this, but I thought it might be good for me to finish off the slides for at least this part of lecture. And we're not going to get to the second half of lecture today, obviously. So I am going to go ahead. So if everyone can take a break from decrypting for a moment, I'm going to go ahead and talk a little bit about ciphers in general again. Okay, so getting started, what have we learned from this encryption exercise? So basically what we're doing is I've been having you guys model communication in an encrypted format. And so when you're sending a message, you're playing the role of Alice. So Alice is sending a message to Bob. And when you're decrypting a message with a key, that's the role of Bob. So Bob knows the key. And so for those of you who had two different things, obviously decrypting was a lot easier with the key, because without the key, you had to sit there and try to figure out what the frequencies were. You had to attack it. You had to try to figure all of that out in order to decrypt the message, right? And so that was really the role of Eve. So Eve doesn't have the key, in theory at least. So the way this would work is maybe you and a friend want to communicate secretly. And so before you start communicating, you arrange ahead of time, okay, I'm going to use the key 5. And if you tell your friend that to begin with, well, then they can decrypt all your messages slowly, assuming you do your math right. But for Alice is going to have to break your cipher and do this weird hard frequency analysis, which is a lot more difficult than just reversing the operation of a key, right? Since applying a key is just modular arithmetic. And so that was the sort of point of this particular exercise. It turns out that this key is actually fairly easy to break. So I know that it might not seem so easy for you while you're doing it, but there are only 26 possibilities. You can brute force it. And furthermore, there are these frequencies that you can use to analyze things. And so there are a couple of weaknesses of the Caesar cipher. It is obviously still a little bit hard to break by hand. You could do it, but it does take some time. But with a computer, it turns out that with a computer, it's entirely trivial to break a Caesar cipher, because you can just have the computer list out all 26 possibilities, look at them, and you'll immediately know which one's the right answer. And so, but it turns out people were breaking these ciphers even back hundreds of years ago. And so people had to come up with with better ciphers or more secure ciphers. And people came up with a bunch of different ways of doing it, some of them involving modular arithmetic, some not. We're going to talk a little bit about the, I'm going to butcher this name, but the Vigenère cipher. And so there are a couple weaknesses of the Caesar cipher. One is that there are only 26 possible keys, really only 25, because if you use a key of 0, that's not a very good key, right? A key of 0 would just involve no encryption at all. And another is you can do this frequency analysis on your letters, which of course is slow, but does allow you to eventually break the cipher. Well, there's another cipher that was invented in the 1500s that fixes both of these problems and uses a longer key. So instead of using a single shift letter as a key, we use an entire phrase, like the phrase magic. Repeat that phrase and then add it using modular arithmetic to the message. And it turns out that this makes the cipher a lot harder to decrypt. In fact, these types of ciphers are super hard to decrypt by hand. And even with a computer, you need to know what you're doing in order to decrypt them. Is the mean always, so is it always mod 26? So it doesn't have to be. So basically, you can do any sort of, any size mod so long as you're consistent and those are the number of symbols. So some people were asking about, well, what about spaces? Well, you could add a space in as a new type of character and have mod 27 instead. Or if you want periods, maybe you can have mod 28 and so on. So it doesn't have to be mod 26. Mod 26 is just the easiest thing to do, which is why we did that in class. Yeah, so let's give an example of the Vigenère cipher. So one of the other groups turns out to have picked the example that I was doing for this quote. So the example I had for this one is, to be or not to be, that is the question. So obviously from Shakespeare. And then what if I want to use a multi-letter key? So the key I want to use is magic. And so I'm going to repeat magic over and over again. And then I have 2 different strings now, right? So I have 2 strings, but you can think of this as an entire encoded message of like numbers 1 through 26. And you can think of magic as also encoded messages of 1 through 26. And then what you do is, in the normal Caesar cipher, you add the same number to every number. But here, with this cipher, you instead add down in each column. And so you would add, to the T, you'd add M. So to 20, you'd add 13, and so on. And so you sum these, and you take the mod 26, and you get some other encoding here. So this is a much more sophisticated encoding, and turns out to be a lot harder to break because each position is encoded by it has a different key, right? And so there's some amount of repetition in the key, but this makes it a whole lot harder to break. And so the encoding for this particular example looks like this. And one of the really interesting things is that if you do the frequencies of letters, frequencies no longer match English. Right? Because even if you had a lot of E's in your original text, each E is in a different position, so it might be encoded to a different letter. And so this kind of positional encoding turns out to be a whole lot more powerful than just the plain Caesar cipher. Of course, you can still decrypt. So decryption is still just subtraction. So you just subtract magic over and over again from each of the different characters. And this kind of cipher is actually fairly powerful. When it was invented, it was considered undecipherable. So back in the 1500s, and it took hundreds of years before people really had the ability to decipher these kinds of encrypted messages. And so these kinds of ciphers were quite popular. Another reason they're popular is because it was very easy to remember your password key, right? It's just some other word. You'd share that word with your friend. Maybe you've decided that your password is going to be math is fun. And if you use that as your password, well, then you don't have to. You can that's all you need to exchange, and then you can send messages to each other and then decrypt, and then things work out fine. Yeah, so I was at one point going to make you guys do this as well if we had lots of time, but it turns out that these things take a lot of time. So we're not going to do this as an in-class exercise. But the basic idea would be I would have had you break up into groups and send each other messages using the Vigenère Cipher, though I would have made you give each other the keys because it would be almost impossible for you to break those keys in the course of a class without using lots of computer assistance. But so the sort of point though is in order to do this kind of communication, you need to have a shared key, right? So if you have a shared key, you can communicate reasonably securely, so long as you both know the same key. Obviously, for Eve, who is eavesdropping, well, they don't have the key, and so things are a lot harder. So it's sometimes they can still crack the code, like if you use a very simple cipher, like a Caesar cipher, you still can crack it, but it's hard, right? And for the more complicated ciphers, it's near to impossible. So the modern ciphers, if you share a key, are almost impossible to crack if you don't know the secret key. But there's a big problem with this kind of method, right? Which is you need to have first communicated that secret key to each other. And well, that's a bit of an issue because if you already have some way of communicating a message, well, then why do you need to have encryption to begin with? And there are a couple of answers to this. Does anyone want to give an example where that might be helpful? Oh, so when might this work for you? So like we have this encryption right now, and in order to do this sort of encryption, both parties need to know what the key actually is. But of course, that requires you to have some way of communicating the key to begin with. So why is this still helpful? Like when might this be helpful in real life? Yeah, like between coworkers. That's a good example. So for example, if everyone in this class wanted to have a secret way of communicating with each other, what you could do is you could just like all come down and then decide on some secret key. And then whenever you like type things out on Discord or whatever, you could encrypt everything with that secret key, and only people who are here would know how to read that message, right? And so it does work so long as you have some way of exchanging the key first and then messages later, right? So if you have a secure communication channel right now, but you don't later, you can turn a secure communication channel now into secure communications later by sharing an encryption key. And then later, when you're on the internet and you don't have security, you can still communicate securely that way. Obviously, Zoom passwords. Yeah, that's another good one where you have just two different media, where you're like, oh, well, I'm going to give you the Zoom password over the phone or by an email, and then presumably someone who's trying to Zoom bomb us won't know that password just from like an outside URL. But yeah, so this is still quite helpful, but of course it doesn't always work. So maybe you're talking to Amazon, and let's say you don't have an Amazon account yet, and so you don't have any sort of way of there's no way for you and Amazon to share any secrets except over the internet, right? So yeah, so the point is that it relies on having a secure way to communicate a secret key to begin with. And yeah, so people are talking about trading nuclear codes. So yeah, so maybe you send a spy with a briefcase. So maybe the United States and Russia want to communicate securely. So maybe they send some spy with a briefcase with a bunch of secure codes over to the other party, and then they can communicate. But of course, this has a lot of issues, which is that if you're trying to communicate with someone you don't know yet, like if you're trying to communicate with some online shopping website who you've never met, well, you don't have a shared secret yet, and so then you can't use encryption of this kind. So then, now the big question is it possible to securely communicate even when Eve can intercept anything you say to each other? So let's suppose that you've just met someone. So Alice has just met Bob, and they want to communicate securely. But the problem is that when they start communicating, Eve has wiretapped everything. So if anything they say to each other, Eve automatically knows. And so they have no way of sending the secure password that Eve doesn't hear. Is it still possible for them to communicate? And obviously the answer to this has to be yes, or all of online e-commerce would not work. And it turns out that the way you do this is really closely related to the modular arithmetic and prime number factoring that we've been working on throughout the class. And I think that I do not actually have time to do that today, since the interactive exercise took a little bit longer than I was expecting, which is fine. Like that was, I think, good, because you got a real hands-on sense of how encryption actually works. And you can also be super doubly thankful for your computers for doing it all for you, so that you don't have to do it by hand every time you want to shop online. But having said that, that's what we'll be doing on Monday. So I will be talking about public-private key encryption, which is really the bedrock of modern, of the internet, really, of secure communication on the internet. Because what it allows you to do is it allows you to communicate securely with someone, even if everything is overheard. Even if everything is overheard, you can still set up a secure communication with each other by using the magic of modular arithmetic and numbers. And can you hack us as a lesson example? I mean, that's sort of what I was having you all do today, right? So when I had you guys decrypt a message without knowing the key, that's one of the things a hacker basically does. Is let's say you're sending your credit card number to a bank. If a hacker could intercept your message there and decrypt it, they would have hacked your credit card number. No, the prof debating to hack us. I'm not sure I understand exactly what you mean by that. But yeah, so the basic point though is that there are ways of breaking these sorts of ciphers sometimes. And sort of the hope is that modern cryptography is strong enough that it's really, really hard for any hacker to do that. And that's sort of what we all rely on whenever we put our social insurance number into some government website. Yeah, and so with that, we will continue, of course, the session on Monday, where we'll talk about public-private key cryptography, and that's really the punchline. That's really the capstone of all the work we've done in this class. So I told you earlier on that I wasn't going to worry about things that were useful. These things aren't going to be useful in your day-to-day life, but they are going to be things that you do use. You just don't have to worry about the math because some computer scientist somewhere has already programmed it into a computer for you. And I think I'll end class a few minutes early. I know today was maybe not the most exciting of lectures, but hopefully you all had fun. There are still mango gummies down here. So have a great day, and I will see you on Monday. Bye, everyone.